Hi, physics. Mr. Janowski here. This is Chapter 13, Homework 3, Problem 4. So what's going on here? Measurements of the light from a distant star suggest that it has about 5 times the mass of the sun. So take astronomy next year. I'll tell you all about how that works. A slight dimming of the starlight every 30 days, and I've already converted 30 days into the time in seconds using field goal posts, suggests the presence of an exoplanet, which is far too dim to observe directly. So, an exoplanet is a planet that is orbiting some star that is not the sun. Exo means like out, so that's an out there planet. So, what is the radius of this planet's orbit? So, first of all, this is actually how we know about most of the exoplanets. When I was your age, we thought there are almost certainly planets around other stars, but we hadn't found any of them. Now we found thousands of them, and typically we find them this way. This is called the transit method of finding the exoplanet. So, real quickly, here's what's going on. So, we're here on Earth. So, here we are on Earth. Way far away, so not to scale, is this star that we're looking at. And going around this star is a little planet. So here's the planet going around the star. Okay. So what happens is we're looking at the star. We can measure how much light we're getting from the star. When this little planet swings in front of the star, it blocks our view of the planet slightly. So, kind of a view of this, like if we're looking at the star, here's like what is actually happening, although telescopes are not good enough to see this. So here's the star. All right, when the planet's off to the side, you're getting the full light of the star. But as the planet swings around, now that the planet's in front of the star, it's blocking that tiny, tiny bit of light. So we can, time out when does that blocking happen. If it happens every 30 days, very reliably, that suggests that, well, something's going in front of it every 30 days. So that's what's going on. But enough about that. That's astronomy and exoplanets. We're going to use Kepler's third law to figure some things out. So what are we actually looking for? What is the radius of this planet's orbit? Okay. So step, what do we want? We want the radius, which is a distance. It's something we can measure in meters. All right. So we're going to use our formula, the pretty version of Newton's version of Kepler's third law. All right. So I always recommend just write the formula exactly. T squared is equal to 4 pi squared r cubed over gm. Okay. The thing we're trying to solve for here is r. So I'm going to switch it. Like first I'm going to solve for r cubed, get a number for r cubed, and then take the cube root of that number. So that's what I'm going to do. So how do I get r cubed by itself? I'm going to multiply both sides by gm. That'll give me gm t squared is equal to 4 pi squared r cubed. Then I'm going to divide everything by 4 pi squared, and ultimately that's going to give me r cubed is equal to gm t squared over 4 pi squared. Okay, so I've just got to put the numbers in here. So big G is what it always is, 6.67 times 10 to the minus 11th. Okay, now mass, this is the mass of the thing being orbited, which in this case is this star, this distant star, and it's got a mass about 5 times the mass of the sun. So astronomers have different ways of figuring out the mass of a distant star. So for the mass, I could figure out this number separately, but I'm just going to do it this way. It is 5 times the mass of the sun, 1.99 times 10 to the 30th kilograms. We'll do the units there. Times t squared. Okay. Well, the starlight, it's every 30 days. 30 days is the period. And I've already done the field goal post for you. So t is 2.59 times 10 to the 6 seconds. And remember, that thing has to get squared. And all of this is over 4 pi squared. All right. You can do this different ways. Or I'll do it this way. A little different than the way I did Chapter 13, Homework 3, Problem 1. I'm going to put the bottom thing in parentheses. That way I'm putting the order of operations correctly into the calculator. And I'm just going to do all of this in one big shot and get an answer for r cubed. All right, so 6.67 EE minus 11 times 5 times 1.99 EE 30 times 2.59. Put the cursor down in exactly the wrong place. 2.59 EE6. And then I'm going to hit the x squared button. So that's going to square just that last term. You can hit enter. I'll hit enter at this point. I've got 4.4519 times 10 to the 33rd. And now I want to divide by parentheses. 4 times pi, and I'm going to hit the x squared button. Then I'm going to close the parentheses. And if I do all of this, I end up with 1.12. I'll write it a little bit more. 7,687, and then 3, so that doesn't round up. Times 10 to the 32nd. Now notice, this is not the correct answer. Okay, why is it not the correct answer? Because I haven't solved for r, I've solved for r cubed. So I need to get the cube root of this number. So how do you get the cube root of a number? On your calculator, different calculators will do it differently. Mine has an x to the box button. That means, the thing you just typed in to the power of is what the box is for. Other calculators will use perhaps a caret button. Like caret on your keyboard is shift 6. Like go up, do the exponent. But mine doesn't have that. Mine has x to the box. So now with this, I'm going to hit x to the box. And to get the cube root of something, you need to raise it to the 1/3 power. So you can hit 0.33333, or you can just hit, x to the box 1 divided by 3, and then you hit enter. And when you do that, you get 4.831287, etc., times 10 to the 10th. And what are the units of this? It's a radius, so it's going to have units of meters. So that's how you do that one. Hopefully you found that helpful.